PN junction diode under forward bias. When external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side to the negative terminal, then the diode is called under forward bias. Here it is shown in the figure, that is positive side is connected to the positive terminal of battery, P side is connected to the positive terminal and N side is connected to negative terminal of the battery. Due to applied voltage, electrons from N side cross the depletion region and reach P side where they are minority carriers. Similarly, holes from P side cross the junction and reach the N side where they are minority carriers. This process under forward bias is known as minority carrier injection. Due to this, near the junction on each, the minority carrier's concentration increases significantly compared to the location far from junction. Due to this concentration gradient, the injected electrons on P side diffuses from the junction S to the other end of the P side. Likewise, the injected holes on N side diffuses from junction S to the other end of N side. This motion of charge carriers on either side give rise to current. The total diode forward current is sum of a hole diffusion current and conventional current due to the electron diffusion. The magnitude of this current is usually in milliampere. Where it is shown the situation, and this is the P type and N type. Holes are injecting in the N side and electron is injected in the P type. And here diffusion of hole and electron is occurs. So I equals to IE plus IS, current due to electron and current due to hole. PN diode, PN junction diode under reverse bias. When N type is connected to positive terminal and P type is connected to negative terminal of battery, then diode is called under reverse bias. This is the case of reverse bias. Yes, P type is connected to the negative terminal of battery and N type is connected to the positive terminal of battery. The direction of applied voltage is same as the direction of barrier potential. As a result, the barrier height increases and the depletion region width widens due to change in the electric field. This suppresses the flow of electrons from N to P and holes from P to N. Thus, diffusion current decreases enormously compared to the forward bias. If the electrons in P side and holes in N side comes closer to the junction due to their random motion, they are swept to maturity zone. This drift of carriers gives rise to drift current, but it is order of few microampere. This is quite low because it is due to the motion of carriers from their minority side to their majority side across the junction. The drift current is also under forward bias but is negligible in microampere when compared with current due to injected carriers, which is usually in milliampere. The diode reverse current is not very much dependent on the applied voltage. Even a smaller voltage is sufficient to shift the minority carriers from one side to other side of the junction. The current is not limited by magnitude of the applied voltage but is limited due to the concentration of minority carriers on other side. The current under reverse bias is essentially voltage independent up to a critical reverse bias voltage known as breakdown voltage VBR. When V equals to VBR, The diode reverse current increases sharply. Even a slight increase in the bias voltage causes a large change in the current. Voltage current characteristics of a diode, VI characteristics. The graph between applied voltage and current is called VI characteristics of a diode. Here it is shown in the forward bias case. This is a PN junction diode. It is connected to a battery. This is voltmeter to measure the voltage across the diode, and this is the milliammeter to measure the current in the circuit, current in the diode, or it is switched to start the circuit on or off. And this is the case for this is the case for reverse bias. Here a positive terminal is connected to the negative terminal of battery. That is P side is connected to the negative terminal of battery, and the N side is connected to the positive terminal of battery. This is microampere or micrometer, and measure the current in microampere, and this is the voltmeter. Now the characteristics of silicon diode is shown in the figure. This represents the forward bias characteristics. Here it is the current and it is the voltage. And this is the reverse bias characteristics. And current is in forward bias characteristics, the current is in milliampere and voltage in volt. But in reverse bias characteristics, current is in voltage is in voltage, and potential difference is in volt, and current is in microampere. Now junction diode as a rectifier. From VI characteristics of a junction diode, we see that it allows current to pass only when it is forward bias. So if is alternating voltage is applied across diode, the current flows only in that part of cycle when the diode is forward bias. This property is used to make the voltage or current unidirectional, and the circuit used for this purpose is called rectifier. Now here is a half wave rectifier. This is forward bias. It is connected to a input alternating voltage. Now when this terminal is positive and this terminal is negative, it is forward bias, so current will flow and we get the corresponding voltage in load. And if this is negative and if this terminal is positive, then it is reversed by, there will be no current output along x and y. So our graph will be like this. For a given cycle there will be output, and for a given half cycle there will be output, and for another half cycle there will be no output, and similarly we go. So we find the output like this. When terminals A is at higher potential than B, then diode is forward bias and hence conduct electricity, and when A is at lower potential than B, the diode is reverse bias and so does not conduct electricity. So in only one half cycle, current flows through the RL, that is load resistance, and we get out voltage across RL. In the next cycle, there is no current through the RL and output voltage is 0. So output voltage or current becomes unidirectional. So this was the concept of half wave rectifier. Now let us see the full wave rectifier. The circuit diagram for arrangement for full wave rectifier is like this: is a transformer. This is a centered cap transformer, and here input is given because input changes direction, and here it is output is transformer output is here we find. Now it is a tap in the center and it is grounded, and there are two diodes D1 and D2 to make full wave rectifier. In one half cycle it becomes forward, and another half cycle, in the first half cycle this becomes forward bias, and in the another half cycle this becomes forward bias. So we get to unidirectional uh, voltage or output. In one half cycle, A is at higher potential than C. A is at higher potential than C. It is connected to like this. So this will be forward bias, and current will flow like this. And A is at a potential C. Also C is at higher potential than B, and C is at a higher potential than B. So current will not flow in this. Current will flow from here to here, and it will go like this. So diode D1 is forward bias and the D2 is reverse biased, and D2 is due to this cause. This is because this is at higher potential. So if we see like this, then it is connected to negative terminal. Higher potential, that is positive value connected to the N types, and negative value is connected to the P type. So it is reverse bias, it is forward bias. So current will flow from this diode, but will not flow through this diode. So diode D1 is forward bias and D2 is reverse bias. Current from X to Y. In the next half cycle, B is at a higher potential than C, and C is at higher potential than E. In this case, D2 is forward bias and D1 is reverse bias. In this case, again current is from X to Y, again from X to like this, X to Y. So we get unidirectional current in the load resistance or output. So we have input like this, but we get output like this. This cycle is due to D1, and this cycle is due to D2. Similarly, this is for D1 and this is for D2. So rectified voltage or current in form of pulse is obtained. Now filter circuit, the circuit which converts unidirectional pulsating voltage into pure DC voltage is called filter circuit. This is the schematic diagram of filter circuit. Here a full wave rectifier is connected, and from this we gives input, and a capacitor is used in parallel to the load resistance. Here we get the output, and from this full wave rectifier we get rectified output, and after passing through this by this arrangement it becomes like this, pure DC converted into a pure DC. Capacitor filter. To use capacitor as a filter, it is connected parallel to the load resistance, that is output. When the voltage across the capacitor is rising, it gets charged. If there is no external load, it remains charged to peak voltage of the rectified output. When there is a load, it gets discharged through the load and the voltage across it begins to fall. In the next cycle of the rectified output, it again gets charged to the peak value. The rate of fall of voltage across the capacitor depends upon the inverse product of capacitance and the effective resistance RL used in the circuit, and is called the time constant. To make the time constant large value C should be large. So capacitor input filter use large capacitors. The output voltage obtained by using capacitor input filter is nearer to the peak voltage of the rectified voltage. Now zener diode. It is a specified purpose. It is a special purpose semiconductor diode which operate under reverse bias in the breakdown region and used as voltage regulator. It is made by heavily doping both P and N side of the junction. Due to this, depletion region form is very thin, less than micrometer, and the electric field of the junction is extremely high, 5 into 10 to the 6 volt per meter, even for a small reverse bias voltage of about 5 volt. The IV characteristics of a zener diode is shown in figure. It is seen that when the applied reverse bias voltage reaches the breakdown voltage Vz of zener diode, there is a large change in the current. After breakdown voltage Vz, a large change in the current can be produced by almost insignificant change in the reverse bias voltage. In other words, zener voltage remains constant even though current through the zener diode varies over a wide range. This property of the zener diode is used to regulating supply voltage so that they are constant. Now zener diode as a voltage regulator. This is the circuit for voltage regulator. We get this is a regulator, rectified voltage we get from unregulated voltage from rectifier, and this is connected zener diode with a resistance, and here a parallel in parallel with the zener diode we connect a load resistance. Here we get output. The curve will be like this. The unregulated DC voltage filtered output of a rectifier is connected to the zener diode through a series resistance Rs, such that the zener diode is reverse bias. If the input voltage increases, the current through Rs and zener diode also increases. This increases the voltage drop across Rs without any change in the voltage across the zener diode. This is because in the breakdown region, zener voltage remains constant even though the current through the zener diode changes. Similarly, if the input voltage decreases, the current through Rs and zener diode also decreases. The voltage drop across Rs decreases without any change in the voltage across the zener diode. Thus, any increase or decrease in the input voltage results in increase or decreases of voltage drop across Rs without any change in voltage across the zener diode. Thus, zener diode acts as a voltage regulator.